Yes. Okay. So as we continue this lesson, we are looking at process for curve sketching. We went through the headings A through H, and we are on letter C here right now, symmetry. We just calculated that this was odd symmetry. So there's going to be some kind of, there's going to be symmetry about the origin. So whatever on one side of the origin sort of thing is going to be mirrored across that point, really. And so we'll look at that a little bit more detail in a bit. So D is next, and D is asymptotes. Okay. What about asymptotes? Well, we didn't have any restrictions on our domain. So that's your first key that, hey, there might not be any vertical asymptotes because that can be anything. So there's no value for x that causes the function to be undefined, which would give us an indication there might be a vertical asymptote. So a polynomial function doesn't have any vertical asymptotes, so there's no vertical asymptotes. And if you take a look at the function again, right, which is right here, and you say, what happens if x gets extremely large? Okay, well, you can do the limits. Okay, that's fine. But if you just think it through logically as well, I'm just going to paste this over here again so we can work with this on another page. If you just think through this, obviously, if x is a billion and x is a billion over here, right? We have a billion to the power of 5 minus a billion to the power of 3. The larger we get, the larger that difference is going to get, right? And it's just there's not going to be any limit at all, okay? And so it's just going to keep getting larger and larger as x approaches infinity, right? Because a trillion to the power of 5 minus a trillion to the power of 3 is going to be a bigger difference than 1,000 to the power of 5 minus 1,000 to the power of 3, right? It's always going to be a bigger difference if the numbers get larger. So that means the graph is going to keep increasing without bound. So we have no asymptotes, okay? Any reasoning that you want to jot down there would be great to just display your communication, but you could say, polynomial function, so there are no vertical asymptotes. You can abbreviate that if you like, and no horizontal asymptotes. Okay, so the limit of the function of the polynomial as x approaches infinity is infinity itself. Like it's just there's no limit. Okay, so as long as you understand that, that's good. And if you communicate that even just slightly, that's great. Okay, so intervals of increase and decrease is the next step. And so what this involves is finding the first derivative. Okay, if you recall, the intervals of increase and decrease. You find the first derivative and you find out sort of where that's positive and where that's negative, right? And so the first derivative for this equation right here is going to be, okay, there's your value there. So we're going to have 15x to the fourth minus 15x squared. Okay, and so where is this positive and where is this negative for a derivative? Well, if you factor that, you take 15x squared out, and you've got x squared minus 1, right? And those factors, we factor that as a difference of squares. We've got this. Okay, intervals of increase and decrease. Of course, you do your sign analysis, and you can find out fairly easily and efficiently where the zeros are. So this factor here is 0 at 0. And it is actually, because this is squared, it's positive before and positive after. Okay, so just remember that that little squared is there. And for this one here, x plus 1, okay, that's going to be 0 at x equals negative 1. Negative before that, positive after. And then at positive 1 here, negative before that, 0, and then positive after. So if you do your sign analysis there, that'll show you that we are increasing until negative 1 and decreasing all the way through to positive 1, and increasing again. So this intervals of increase and decrease also tell us what? F asks us for local maximum minimums. Okay? And so one of the ways we did this early on in the chapter is by looking at our sign analysis. So E and F really go together. We did talk yesterday about how the second derivative, you can find out if you have a local max or min at a critical number by plugging that critical number into the second derivative. But we don't even need to get to the second derivative here yet. We can see right from E that we have a local what? What is this right here? That's a local, yep, a local max at. Now, you should put in the points here. So it's obviously it's x of negative 1. So you could put this, f of negative 1. And what does that equal if we plug in negative 1 into the original? I think we calculated it already. What was that? Negative 2? Positive 2? Okay. So local max at, and this is the point, negative 1, 2. So that's going to help us in our curve sketch as well, right? We know we have a max here somewhere, right about there. And we have a local min. Do we have a local min at 0 here? Here's another critical number, so we have a local max or min here? No, why not? Yeah, very good. Okay, so at 0, it looks like this. It kind of comes down, and then, but it does not turn back up. So we don't have anything there. So yeah, you're right. That's what it's going to look like there. So look at all this we're doing here so far. Look at this. We're piecing together a few things here, aren't we? The local min is going to be at f of positive 1 equaling negative 2. That's the point 1, negative 2. So we've got a whole bunch of things happening here. This is pretty cool. You're starting to get the view of this graph, right? And did we find out some x-intercepts? Yeah, we did find out some x-intercepts from before. So we'll place those in a bit. Gotta finish this lesson here. Okay, so what's next? We just do have one more, right? G. Now, G is concavity, okay? So we do have to find the second derivative. If we take the derivative of the derivative, again, what we get is 60x cubed minus 30x. If we factor that, we can take out a 30x out of there, and we're left with 2x squared minus 1. To find out our concavity, we want to do sign analysis. So again, we'll do sign analysis here. Okay, so as a difference of squares, here are your factors here. You're going to have 0, minus, plus. All right, this one we said is going to be at negative root 1 over 2. That's going to be a 0 there. Plus, plus, plus. And a positive root 1 over 2. Going to be a 0 for this factor. The second derivative then will be negative 0, positive 0, negative 0, and positive. So this is our concavity, and these are the points, the x values for the points of inflection. All right. Now, just to expedite the rest of this, you put all this together, and it's going to look like this. Okay. So you're going to have your intercept here. You're going to have a local max here and a local min here. The points of inflection are going to be about here and here. All right. More intercepts over here and over here. You put this together, there we go, concave down, concave up, concave down, concave up, and intercept, concave down and intercept. We have symmetry about the origin. You would label your max and min points, and you would label your points of inflection and your intercepts, okay, which I will finish on the video in a few minutes, but this is sort of what your graph looks like, piecing it all together. So process for curve sketching, the headings A through H. And so here are your labeled points for your graph, intercepts, maximums, inflection points should be labeled, And that's the completion of your A to H for sketching the curve using your calculus methods.